things. We have to notice something. Okay? I know, it's hard. I promise I couldn't. Okay. So, we're going to notice that if f, oh, maybe I should give you some coordinates for f. So let's say f is p comma q. Okay, so I'm really thinking, right? F's a vector field, it's a function of x and y. And it's given in vector coordinates by p of x and y and q of x and y. Right? And what's convenient about these sometimes? Like, which vector fields are the easy ones to deal with?
Gradients.
Yeah, if they're gradient of something. So if f, the vector field, p comma q, is the gradient, and I'm going to call this function g for now because I'm worried that I'm going to confuse the words. So I've got f, which is a vector field, and g, which is the what they call a potential function, right? Or kind of the antiderivative. You guys cool with that?
Yeah.
So if this, then what?
The vector field is path independent.
Okay, perfect. It's path independent, right? How do I know that? Like, what's your tool for establishing path independence for vector fields that fit the gradient or something?
Thing we just said.
No. You have a thing for this. It starts with a F.
Function.
The fundamental theorem of line integrals.
Yeah, the fundamental theorem of line integrals is what tells you this, right?
Okay.
Right. Fundamental theorem of line integrals tells us that these are path independent. Okay. It was so convenient for things to be path independent, right? That maybe I should think about this a little harder, right? So that I could establish if something was the gradient a little bit quicker, instead of having to go through this rigmarole of finding the potential function. You guys see that? Okay, so f is path independent. What else do I know? Like, for instance, what's p?
Partial with respect to x.
Yeah, p is the partial of g with respect to x, and q is the
Partial with respect to y.
partial of g with respect to y. And if there was an r, right? If there was a third coordinate, what would that be?
C.
Yeah, that would be the z partial, right? I'm only going to play in 2 dimensions today just because I want to keep this a little simple, but we could play this same game. All right, so these two guys are the partials, and here's the thing we have to notice, right? So the question I want you to ask yourself is, what do we know about gxy and gyx? So what are these two things? Do you guys remember?
Oh, g of x, y.
Yeah, so these are
derivative.
g sub xy, which is the,
Partial derivative of x, and then partial derivative of y.
yeah, so this is the partial with respect to y of the partial with respect to x of g.
Well, they're pretty much the same thing.
Yeah, and it's usually the same thing, right? So that should answer, what do we know about these, right? Well, what I know about them, right, answer is they're the same.
If it's a gradient.
Yeah.
So I'm not asking about, right, I'm not asking about f right now. I'm just talking about this function g, right? So the mixed partials of g, right, are equal when things are reasonable, right? And for reasonable, right, we mean when the second order partials are defined and continuous. You guys cool with that? What does that mean?
The test for finding, to see if you can use the FT and LI, you can just see if the mixed partials are the same instead of having to work out all the funny business.
You guys see that? Instead of making a couple potential F's and trying to balance, right? I could just check if well, what are G sub xy and G sub yx in terms of P and Q?
P prime, Q prime, or with the partial of P with respect to Y.
Okay, so the partial of P with respect to Y, right? And when I do that, I'm thinking G sub xy, right? Right, that's the y derivative of the x thing. And I'm wondering, hey, is that the same as the partial of
Q with respect to X.
Q with respect to x? And what I'm thinking there is G sub y x, right? Okay, and I end up with this little thing, right? So let me rearrange this just slightly. So this is just an algebra rearrangement. Got the partial of Q with respect to x minus the partial of P with respect to y, and that's going to be 0. This thing being the, we call this the curl. Okay. And what was I kind of trying to phrase? And I don't quite have the thing I want, right? The thing I want is the curl 0, then the fundamental theorem of line integrals applies, right? And what I actually have here is not quite that. What I have here is if the curl isn't 0, then the fundamental theorem doesn't apply. You guys see that? That's really what I found. So the kind of summary of this is if the partial of Q with respect to x minus the partial of P with respect to y isn't 0, then F isn't the potential, isn't the gradient of a function.
And that's just how the proving works. Went from, if it is, then this happens, but we can't necessarily go backwards.
Yeah, exactly. So this is the converse of the statement I would really like, which says that if the curl is 0, then this is the gradient of something. That's a little bit harder to demonstrate, but it's also true. Okay? So what I want to give you guys is just a flavor for the thought process here, and a little warning, right, that this isn't actually the thing I'm going to say. The thing I'm going to use is I'm going to test, hey, is the curl 0? If the curl's 0, I can find a gradient. If the curl's not 0, I can't. Cool. But that's not quite what I demonstrated here. You see that? Okay. It should be noted that all of this depends on the second order partials being continuous. You guys see that? The second order partials aren't continuous, all bets are off. This doesn't do you any good.
So if it does equal 0, then it still might not be the function that we're looking for?
It actually is, but this doesn't demonstrate that.
Okay.
Yeah, so maybe I should add that in here in a different color. So not demonstrated here is the other statement, which is the one I really kind of want, or the other half, which is that if the curl of f is 0, then f is the gradient of something. Or a function. You guys see that? That's the thing I really wanted. That's not the thing I demonstrated here, but it's also true. Cool. That thing's a little bit harder to demonstrate, so I'm going to gloss it, but go ahead.
And we say,
Okay. We could actually make a decent proof of this. It's within the scope of tools we have. It just takes a little bit of time. Cool. Of course, all of this is predicated on the idea that the second order partials are continuous. Again, if the second order partials aren't continuous, neither of these statements is even close to reasonable. Cool.